Alright, so in this video, I'll be checking whether the polynomial 8 plus 7x minus 2x squared plus 3x cubed, so this polynomial, whether this polynomial is a linear combination of the following two polynomials, that is h of x, which is equal to minus 3 minus 5x minus 2x squared plus x cubed, and g of x, which is equal to minus 9 minus 4x minus 5x squared plus 3x cubed. In other words, I'm asking whether I can write p of x as a linear combination of h of x and g of x, i.e. can I write p of x as a scalar c1 times h of x plus a scalar c2 times g of x times g of x. Now so far we've dealt with vectors as linear combinations of themselves and matrices as linear combinations of themselves. It's pretty similar for polynomials. So there's a specific way that I like to do it that I think is visual and that I think is easy for people who've just started linear algebra. So I want to know if 8 plus 7x minus 2x squared plus 3x cubed can be written, so is it equal to c1 times minus 3 minus 5x minus 2x squared plus x cubed plus c2 times minus 9 c2 times minus 9 c2 times minus 9 minus 4x minus 5x squared plus 3x cubed. 3x cubed. So I sometimes get confused when I sort of see like this much information, because this is a lot to take in. But basically, the easiest way of creating, because now you need to create a system of linear equations, right? That's the whole point of writing it like this, is I want to solve for C1 and C2, so I want to create a system of linear equations. So the way I like to do it is I like to separate each equation by the degree of their exponent, or by their sort of their algebraic representation. So what I mean by that might sound confusing because it probably isn't clear, but what I mean by that is, for let's say for 1, I want to know if 8 can be written as c1 times minus 3 plus c2 times minus 9. Okay, now why 1? Well, because 1 can be written as 8 times 1, and minus 3 can be written as minus 3 times 1. Similarly for minus 9. Okay, so what's my point here? Well, I can also do the same for x, right? I can say 7, instead of writing 7x, where you have 3 variables and it's kind of confusing, well, the second variable is kind of confusing. It's sort of like I'm factoring the x for the whole equation, and I'm left with is 7 equal to c1 times, and I look at which of these expressions, which of these coefficients are connected to x. So in this case, it's minus 5 and minus 4. So c1 times minus 5 plus c2 times minus 4. And then similarly for x squared, so my x squared here has a coefficient of minus 2. So minus 2 is equal to, and now I have minus 2x squared and minus 5x squared. So is minus 2 equal to c1 times minus 2 plus c2 times minus 5. And finally I have x cubed. So I have, on my left hand side, I have 3. So can 3 be written as a combination of C1 times, well, in this case 1, so C1 times 1 plus C2 times n. Which coefficient here has x cubed? Well, in this case, it's 3. So C2 times 3. So now I have a system of linear equations. So this is my system of linear equations. So in this case, what I think I'll do is I'll put these in a matrix. You get a 4 by 2 if I don't include the row of constants. So this is C1 and C2. So I'll get minus 3, minus 5, minus 2, 1, and I'll get minus 9, minus 4, minus 5, 3. And then on my right hand side, or I sort of switch the sides, but I think you can get it. On this side of the constants, I'll get 8, 7, minus 2, and 3. So now what I'm going to do is I think I'll do some row reduction. So I'm actually going to use the last row, which is a bit unusual, but you'll see why. So I'm going to use this last row, and I'm going to get rid of all the coefficients here. Okay, so I'll do row 3 is equal to row 3 plus 2 times row 4. And then I'll write row 2 becomes row 2 plus 5 times row 4. And row 1 becomes row 1 plus 3 times row 4. Because you remember from Gaussian elimination, or if you haven't, no, you've probably already done Gaussian elimination at this point, Gauss-Jordan elimination. I'm just getting rid of my coefficients here. I'm trying to get them to be 0. Okay, so what that becomes, so this stays the same, 1, 3, 3. Then this is 0, and this is 1, and this will be 4. Then I'll get 0, and then I'll get, let's see, 11, and oh, that's a big number, 22. And finally here, so this is where I get a problem. So minus 3 plus 3 is 0, and then minus 9 plus 3 times 3 is 9, so minus 9 plus 9 is 0. But on the side of my constants, I get 8 plus 9, which is 17. Okay, so I can actually stop here in my row reduction, and I can say that because of this, I basically have an inconsistency, because this, what it actually means, this means that 0 is equal to 17, which is impossible. This is not true. This is impossible. Impossible. But that's what my linear equation, or my system of linear equations, gives me. It gives me an impossibility, which means, as you know, that my system is inconsistent. My system is inconsistent. That means that it has a contradiction, or something that can't happen. In this case, 0 equaling a non-zero number. So since my system is inconsistent, this means that my polynomial, remember my polynomial, I called it P of x. So that means that my polynomial P of x, cannot be expressed as a linear combination of g of x and I believe I called it h of x, g of x and h of x. So I can't express p of x as a linear combination because I get an inconsistency, or an inconsistent system in my row reduction.